Welcome to the video on radical algebra. Let's start by comparing two phrases you may have heard before, radicals and square roots. Let's examine what the square roots of 49 are. I'll tell you what I mean by that. But before I do, this s, the fact that it's plural, is very significant. There is more than one square root of 49. The square roots of 49 refer to all numbers which, when squared, the result is 49. Well, clearly 7 squared is 49. That I got by just guess and check. But it turns out negative 7, when squared, is also 49. You'll recall that a negative times a negative is a positive. And so there are two numbers that, when squared, are 49. So we say the square roots of 49 are 7 and negative 7. Sometimes we're only interested in the positive square root because any positive number has two square roots, a positive and a negative. So when we only want the positive square root of 49, we're not interested in the negative, we refer to that using this symbol. And of course the result is positive 7. Now, we came up with the word radical so that we wouldn't have to say the positive square root of. So now we just say radical 49 is 7. So what is radical algebra? To illustrate that concept, consider the following example. Let's consider radical 12. This means, of course, the positive square root of 12, which is the same as to say that positive number, which when squared, the result is 12. Well, how can we square a number and get 12? A lot of students would think it was 6, but of course 6 squared isn't 12. You can find a decent decimal approximation for this by guess and check. I guessed enough numbers until I discovered that 3.461 squared, or times itself, is very close to 12. And then I guessed a decimal slightly higher than that, 3.462. And when I squared that, I got something higher than 12. And one could try numbers in between, but if you restricted yourself to rational numbers or decimals, you would never find anything that when squared is 12. But we've created a real number system where we can find radical 12 by simply calling it that number which when squared is 12. But for now, let's just leave it as a decimal approximation, because I want to paint a picture for you for what radical algebra is. It turns out, if you take a radical, you can often express it as another expression that involves a different radical. This, by the way, 2 radical 3, and I don't expect you to know where I got that from, turns out to have the exact same decimal value, if you will, as radical 12. Now, there's nothing here showing you how I figured this out. I'm simply pointing out that in mathematics, there can be 2 different looking expressions that have the same value. And if those expressions involve radicals, then we say that radical algebra is the act of converting one expression into what we might consider a simpler expression. Now, this is not an example to show you what radical algebra is, just to give you the concept that radical algebra is to take a radical expression, turn it into another radical expression, both of which would have the same decimal approximation. Before we can do any actual examples, we have to establish 3 fundamental concepts in radical algebra. The first of these is known as reducing radical terms, or just reducing terms. A term, by the way, is a non-radical times a radical, and that's what we mean by a single radical term. By the way, before we reduce this term, it's worth noting that sometimes we put the times sign in between the whole number and the radical, and sometimes we don't. And you have to be flexible about not demanding that you see the times sign all the time, because you probably won't. So back to this problem. Radical 72 is clearly a decimal. There's no whole number times itself that equals 72. Nonetheless, we would deal with expressions like this in algebra all the time, and we want ways to reduce them. And what does reducing mean? Well, it means to make the number inside the radical, also known as the radicand, smaller. So how can I make the number under the radical, or the radicand, smaller here? Well, I'll show you a trick. What you can do is take this radical and factor it. It just so happens that 36 times 2 is 72. We're using something called the multiplicative property of radicals here, or in short, radicals multiply, or can be factored to reverse the process. Now, once we've gotten it in this format, we can take radical 36, recognize that, oh, that's a whole number. Radical 36 is 6, because of course 6 squared is 36. And once we simplify the radical in that way, we can multiply the whole numbers together. 5 times 6 is 30, and we now have a simplified radical expression. What makes it simpler? Well, the number under the radical, or the radicand, is smaller, and we value that in algebra for whatever traditional reasons. And that's what we mean by reducing a radical term. By the way, if you were wondering, back when we factored 72 into 36 times 2, if it crossed your mind that there are other ways to factor 72, then good thinking. Watch as I do this problem a different way. Suppose instead I had factored 72 into 9 times 8. Let's examine what would have happened. Radical 9 is 3, and 5 times 3 is 15. Well, that doesn't look like the same answer. But it turns out all three of these expressions, the ones at the bottom of each column and the original expression, are all the same. Now, 15 radical 8, it turns out, can be simplified further, because after all, I can express radical 8 as radical 4 times radical 2, but radical 4 is 2, and now I can multiply the whole numbers. 15 times 2 is 30, and thus showing that even if I had chosen a different factorization in the beginning, I would have got the same result in my final reduced form of this term. So that's fundamental principle number 1, reducing terms. Fundamental principle number 2, multiplying terms. Suppose I were to multiply these two radical terms together. Now, of course, each one of these radical terms can be expressed as a decimal in its own right, but the traditions in algebra have us avoiding decimals to see how we can simplify expressions without decimals or calculators. So in that tradition, let's see what we can do here. Well, one thing I could do is realize that this is really just the product of 4 numbers. And as such, I can rearrange the order of multiplication. That's called the commutative property of multiplication. And furthermore, I could multiply the whole numbers together and the radicals together, thus expressing this as 21 radical 30. So when we say we're multiplying radical terms, that's what we mean. Essentially, you multiply the whole numbers together and the radicands together. Which brings us to fundamental principle number 3, combining like terms. Here's an example. Now, in this particular problem, you'll notice there's 3 multiplications. They're not written, but there's 3 multiplications and 2 additions. And generally speaking, multiplication comes before addition. But since I'm not interested in using the decimal equivalents of radical 2 or radical 3, which I could do if I wanted to crunch this entire expression down into 1 decimal, then there's no way to perform those multiplications. But here's an interesting trick. What if I rearrange the order of the terms? What if I took the first and last terms and put them together? Well, we know we can rearrange the order of addition, and that's That's another commutative property. And so by doing so, I can employ an interesting trick. Notice the first two terms on the left of the bottom expression. You may see them in red. Both of those terms have a factor of radical 2. Using the distributive property, I can factor out a radical 2. I could have written it in front of the parentheses as well, but tradition dictates that I write it afterwards. Not that that matters. The important point is that once I've factored a radical 2 out of those expressions, I can simplify the 4 plus 7, and that ultimately gets me to one term with a radical 2 instead of originally 2. And by rearranging the terms in their order and using the distributive property, we can combine like terms and simplify the expressions. Now, none of these are necessarily problems that you would encounter on your own in an algebra course, although you might in the easy cases. But each one of these three fundamental processes is going to be the basis for some more complicated examples that we're going to see in the remaining part of this video. So let's take a look at our first example of many, as you can see here. Sometimes when students look at radical expressions, they just see a bunch of weird-looking symbols and don't know what to do first. One of the most important skills you can have in radical algebra is to try to imagine an expression that is simpler but has the exact same format as the one that you're analyzing. If you look at the algebra problem on the right, your algebraic intuition might tell you to distribute the x into the parentheses. In other words, to multiply x times y and x times z. Well, if that's your algebraic thought, then follow that same logic when doing a radical problem. When one sees this problem, one should think, I'm going to distribute what's outside the parentheses into the parentheses. Now this turns out to be the result, and let me explain. First I multiplied the 3 radical 2 times the first term. Hit pause if you want to analyze this. Here are the particular details. Next I multiplied the 3 radical 2 by the radical 2, and I got 3 radical 4. Here are the particulars. Now one might think that we could stop here because we have two expressions and there's no way to factor out a radical because they're different. But the challenge of the three fundamental processes that we saw in the beginning of this video is that you have to employ them strategically throughout these problems to try to get a more simplified expression. So while you may be tempted to quit here, it turns out we can go further. Let me explain each term. 15 radical 12 simplifies to 30 radical 3. Why is that a simplification? And how did I get it? Well, why is it a simplification? Because the radicand is smaller. How did I get it? Here are the particular details. I used the fundamental principle of reducing terms. Hit pause if you want more time to analyze this. Similarly, I reduced 3 radical 4 to 6. Here's the details. And now that I've reduced the radicals as much as I can, I have no like terms to combine. There's nothing else I can do to simplify this expression. Now I'm done with this problem, but there's a noteworthy comment about the problem and the answer. I worked out the problem and the answer on a calculator here, and both of them worked out to 45.962, approximately. So why am I bothering to take the top expression, whose decimal value is 45.962, and simplifying it to the bottom expression, whose decimal value is also 45.962? Well, that's the tradition of algebra. We take symbols and manipulate them into easier or more recognizable symbols. And that's a tradition that you need not only in algebra, but to go further on in mathematics courses. That being said, let's move on to the next example. Suppose we wanted to do this problem. Again, sometimes you can look at these and see so many radicals that it seems like a nonsensical expression, and there doesn't seem to be any clear indication on what to do. Well, imagine that without the numbers or the radicals, that we had an algebraic expression of similar form, as you can see here. Well, if you had an algebraic expression like this, you would try to combine like terms. So I'm going to focus on that here. There doesn't seem to be any like terms in this expression. After all, the radicands are all different. We can only combine like terms if the radicands are the same, using the distributive property by factoring that radical out. But what you may not have noticed right off the bat is that 4 radical 24 is simplifiable. So how did I get 8 radical 6? Using fundamental principle number 1, reducing. Hit pause if you want the details. And by changing the radical into a lower radicand, I've not only simplified the problem, because 6 is less than 24, but also I happen to notice that I have 2 radical 6 terms in this expression. And because I have 2 radical 6 terms, I can put them together. It doesn't matter where. But by putting them together, I can factor out a radical 6 here, which ultimately will lead me to this as my final simplified expression. Here are the details on me factoring out the radical 6. So again, we're not solving equations here. We're just manipulating symbols to make less symbols. That's called simplifying, and it's a very important skill in algebra. Now let's take a look at another example. So again, this may look like a bunch of radicals crammed into a confusing expression. But if you stop and think about what's happening here, think about this as an algebra problem without the radicals, then you quickly realize that this is just a FOIL problem, if that's what you are used to calling it. It's essentially a multiplication of binomials. And so we're going to use the same process here with the radicals that we would have if these were just algebra symbols. Now this turns out to be the next line. Let me explain each of these step by step. First, I multiplied the first term by the first term. You can pause for details. And that gave me 18 radical 5. Then I multiplied the outer terms. Pause for details. That gave me 3 radical 50. Then I multiplied the inner terms. Here are the details. It's worth noting here that when we have an expression like radical 2 times 6, we typically write the whole number first, so we would write this as 6 radical 2. Not that you have to. And that gave me this. And finally, the last term of each pair multiplied together gives me negative radical 20. Now, I'm not done with this problem, but it's worth noting here that I've essentially used the FOIL or multiplication process, just like I would have in an algebra problem that had no radicals, to expand this expression. Now, at this point, I wouldn't necessarily call this a simplification. It looks worse and has bigger numbers under the radical than the original expression. But it turns out there's more that we can do with this. For example, we can simplify 3 radical 50 into 15 radical 2. Here are the details. We can also simplify radical 20 into 2 radical 5, and the details are shown here as well. So now I've gotten the radicals smaller again, but one still has to question whether this is a simplification of the original expression. It doesn't look much simpler. But it's about to become so because I can rearrange the terms. Notice I have two terms that have a radical 5 in them, and I have two terms that have a radical 2 in them. So all I've done here is rearrange the order of addition. And in so doing, I can now get my final result here. This result, by the way, came from combining these two terms. Here's me using the distributive property to combine those, and similarly combining the last two terms, and there's the distributive property showing that as well. So as you can see, these problems can get quite messy, but they all come down to four basic ideas. The three fundamental principles that we saw earlier in this video, combined with your basic knowledge of algebra rules as they pertain to non-radical expressions. And if you combine those basic algebra rules with the three basic principles of radicals and keep simplifying till you can't go any further, you can simplify any radical expression that you're given. So here's another example. Suppose we were going to take this two-term radical expression and square it. Well, as you know from algebra, although many people don't know this, exponents do not distribute. Very common misconception that they do. So how do we square something with two terms if we can't distribute an exponent? Well, we multiply that thing times itself. And we use the same FOIL process, multiplying pairs of terms, just like we did on the last problem. Now, I won't show as many details here, but these are the four terms you get. Pause if you need to convince yourself of each of these. And once we've multiplied the terms out, we can reduce those that are reducible. Again, pause to see the details on your own if you'd like to here. The overall point being, now that I've done this, I can rearrange the order of terms, putting like terms together, combining those like terms to get a much simplified expression compared to the original problem. I'd like to look at another example of multiplication of two-term radical expressions. And without giving a ton of detail, and simply saying that I used the same FOIL process that I did on the previous problems. Pause if you want to see the details here. But what's less interesting than or more interesting than the details is that we end up in this problem with a single rational answer. In other words, an answer with no radicals in it at all, to this multiplication problem of two irrational numbers. And what's worth noting here is that this happens whenever you multiply what are called conjugate pairs. Conjugate pairs are any two-term expressions with opposite middle signs, which are otherwise identical. So to summarize, when you multiply a radical expression times its conjugate pair, you get a rational number. Worth noting for later. Let's change the subject a bit to the concept of a radical multiplied by itself. And I want to use this as an example. Now, we don't particularly know what x is in this expression, nor do we care necessarily. But what's worth noting here is that we have a radical multiplied by itself. Well, as we know, radicals multiply together. So I would have to multiply 2x plus 5 times 2x plus 5 using the FOIL process. And ultimately, after combining terms, getting this. But how could that be simplified? Well, let's think about what it means. It means what multiplied by itself would equal 4x squared plus 20x plus 25. Well, of course, 2x plus 5 multiplied by itself would be that. We just worked that out. And therefore, the answer to this radical simplifies to 2x plus 5. Now, people rarely do the work here, so let me just give you the punchline. When you multiply any radical times itself, you get the radicand without the radical. That's an important finding. Let's use that finding to do this problem. Now, up till now, we've mostly done only problems that are purely numerical, but radical expressions can have variables in them as well, of course. So if we wanted to square this, we would have to multiply the entire thing by itself. Remember, exponents don't distribute. So let's commence the FOIL process. Well, first I'll show you the next line in this calculation, but now let me explain where all of that came from. I multiplied the first times the first, but that's a radical times itself. So that just gave me this quantity here. I didn't really need the parentheses. I just put them in to show you that it was a single result of the f part of FOIL. Then I multiplied the outer terms and got this. Then the inner terms and got this. And finally, -2 times -2 is +4. Now that I've performed the multiplication, I'm going to look for simplification. The first one that jumps out at me is that I can combine the two radical x plus 3 terms using the distributive property or the rule for combining like terms. Notice I simply combine the coefficients. -2 plus -2 is -4, leaving the radical alone. And finally, I can add the 3 and the 4 together to make 7, and I have a simplified version of the original expression. And the final concept in this video is about rationalizing the denominator. A rational number is basically a decimal, but since most radicals aren't exactly expressible in decimal form, they can be approximated that way, but because they're not exact decimals, radicals are often thought of as irrational numbers. In most cases they are. And so when you see the phrase rationalize the denominator, instead you should think, get the square root out of the denominator. Well, how are we going to get the square root out of a denominator when there's a square root in the denominator? Well, it turns out there's this cool trick called multiply by 1. So what I'm going to do is take the original problem and multiply it by 1 in the form of radical 5 over radical 5. Now, why would this help? Because the denominator, when we multiply across, will now be radical 5 times radical 5, which is 5. So what have I done here? I've taken this expression and turned it into one that's not quite as simple. It has more stuff in it. It doesn't really feel like we've simplified here. But the expression on the left, the so-called original problem, has a radical in the denominator. We've traded that in for a radical in the numerator on the right. Why is that superior? Well, there's a long history behind that. This video won't go into, but suffice it to say it's an algebra tradition, whenever possible, to get the radicals out of the denominator, which most of the time means replacing them into the numerator in some fashion or another. But that's what we mean when we say rationalize the denominator. There's no longer a square root in the denominator. And lastly, let's look at a denominator with two terms and a radical in it. Again, it's sort of against algebra tradition to have a radical in the denominator. So again, I'm going to use an awesome multiply by 1 trick to get rid of that. But look at the one that I've chosen. If you see it in green, the fraction on the right does definitely have a value of 1. After all, anything divided by itself is 1. But why would I want to multiply by this particular one? Well, it turns out there's two terms in your denominator. You want to choose the conjugate to multiply that by, and then replace that with the conjugate over itself. And if this seems a little strange to you, it's because you maybe haven't seen this before. What happens here is that when you multiply out the denominators, you get 14.
Well, how could all that multiply out to be just the number 14? Well, going back to the multiplication of conjugates having a cancellation of radical terms, you can see why somebody would choose to multiply by this green version of 1 that you see there on the right side. And so what have we done here? Well, we've turned an expression with a radical in the denominator into an expression without radicals in the denominator. Have we simplified it? Not really. Look at the top line and the bottom. We really can't say that the bottom one is simpler, but for algebra tradition's sake, get the radicals out of the denominator. An interesting story as to why, and we won't go into that here. And that completes this video. Thanks for watching.